We're going to start talking about double integrals now. Okay, so we'll kind of define them and then take a look at some basic ones. But first, let's just review in Calc 1 the definition for an integral. The definite integral from a to b of f of x dx. I think we all remember that it represented what? Okay, yeah, you're thinking fundamental theorem. What does it represent, big picture? Area under a curve. Okay. So, area under the curve from A to B. So something like, we have f of x looks like that. Here's our interval from A to B, and we're talking about the area under the curve. Okay? Now, you also defined it if you partitioned the interval into several points and separated into little tiny rectangles. Does this look familiar?
Yes.
I think we called those the Riemann sums. Okay? So you can partition this into as many rectangles as you want, and as you partition them into an infinite amount of rectangles, that's what this limit represents, you just add the sum from k equals 1 to n of the area of all those tiny little rectangles, and the area of those rectangles would just be base times height. The base would be delta x sub k, so that's the width of each little rectangle, and then the height would just be the value of f of x, so we'll do f of x sub k, and in the book they like to use a star notation to indicate a particular, any particular height as opposed to a specific one. Okay? So that's the Riemann sum version of the definition. Intuitively, you should just, you guys all knew it was the area under a curve. Okay, so now, if we extend this into Calc 3, now, instead of an area under a curve, we're going to be finding a what? A volume under a surface, that's right. So now, given a function of two variables that is continuous and non-negative on a region R in the xy plane, we can add that in. The volume problem will be to find the volume, as you guys stated, of the solid enclosed between the surface z equals f of x, y, and the xy plane. So imagine we have some surface. Bless you. Here's our three-dimensional coordinate system. And let's say this is our region R. Okay, so the idea that we used earlier where we partition it into little rectangles is pretty much going to be the same idea here, but we're going to start with partitioning the region into little rectangular regions. So maybe something like this. And now what we'll do is take a point right in the center of one of these little rectangles. We'll call this point x sub k star, y sub k star. And then if we map that to the surface, now that corresponds to a little patch here, another little rectangle there. And that value will be f of x sub k star, y sub k star. So if you just plug in that point from the region R, that'll tell you the height. And we can approximate the volume by making a little parallelepiped here. And if we do that over the entire region, I think you get the idea. So here's this three-dimensional solid. And if we partition the region R into tiny little rectangles, and we take a point in that rectangle right in the middle, map it up to a corresponding height, then we can form a prism or a rectangular prism or a parallelepiped generally. And if we take the limit as we decrease the partitions in size so that we go to infinity, we can approximate the volume. Okay, so that's the notion behind the definition. Let's write that down. We can approximate the volume with rectangular parallelepipeds. We know the volume is just going to be the area of the parallelogram or rectangle times the height. We'll call the area of that delta A sub k, as opposed to a width, which was delta x sub k before. The height, which used to be f of x, up here, right? Now the height of the parallelepiped will be what? Right. Okay, so this will be the approximate volume. Okay. If we take the limit as n goes to infinity, of that, and we add all those volumes together, I'm going to switch the order and put f of x first. This is the formal definition using a Riemann sum for the volume problem. Okay. Now, if, we can just add this in there, but it's the same idea as in Calc 1. If the surface, I mean in my picture here, the surface is entirely above the xy plane. If the surface is above and below, then the Riemann sum would be the difference in volumes. The difference in volume above the surface, or the xy plane, and then below the xy plane. Okay? So, if f has both positive and negative values, then it's the difference in volumes between R and the surface above and below the xy plane. Okay? And now this volume, so now if we connect it to integrals, becomes a double integral as opposed to just one. We use R to define the region. So instead of integrating over an interval from A to B, we're going to have a region R that we're going to use as our bounds of integration. So that'll go underneath the integrals. We'll have our function, just like we did before, f of x. Now it's f of xy. And instead of dx, we're going to use dA to stand for area. Okay, and again, that's the limit as n approaches infinity. So we'll put it all together here. Of the Riemann sum from k equals 1 to n of f of x sub k star, y sub k star times delta a sub k. Okay. You should know where this definition came from and how all the notation fits together. Okay. So, as far as evaluating double integrals, we'll start easy today. You're just going to use what we call iterated integration. So if we have the integral from a to b for the inner integral and then c to d for the outer integral, okay, this area will become dx dy once we have a definite integral to work with. The way you would evaluate it is by first figuring out the inner integral. So the integral from c to d is still going to be there, but what you're going to work with is this first one, the integral from a to b of f of xy dx. You're going to compute that first. And once you figure out that integral, then you'll just be left with a single integral, and you'll integrate one more time. Okay? And of course, these are interchangeable. Okay? So if we have double integral of f of xy, let's say dy dx first, same idea. Start with the inner integral. Evaluate that first, and then you do the outer integral with respect to x. Okay? So let's try an example here. So here is a surface, x squared y. You don't necessarily have to know what it looks like, but know it represents some surface. Y is between 1 and 2. X is between 0 and 3. Okay. So if we start with the inner integral, if I integrate with respect to y first, what is x squared y going to become? That is correct. 1/2 x squared y squared. So you just treat the x squared for now as a constant. So integrate y, you get 1/2 y squared. And then that is from y equals 1 to y equals 2. And I do like to write the y's here so I don't get confused as to where I'm plugging in. Sometimes I've seen that mistake before where people will plug into the wrong variable and then things fall apart. So make sure you know where you're plugging things into. If you plug in y equals 2 to y equals 1, if you plug in 2, let's see, that becomes 4 times 1/2, so 2x squared minus, plug in 1, that'll just be 1/2 x squared. Two minus 1/2, that's the same as 3/2 x squared. So now we're just left with this integral from 0 to 3. If you integrate 3/2 x squared, That'll be x to the third divided by 3. So the 3 halves, or the 3 cancels, and you get 1/2. And this is from x equals 0 to x equals 3. 3 cubed is 27, so 27 halves minus 0. So this would be the volume, 27 over 2. Okay. Why don't you go ahead and try this integral, but let's just switch the order here. Take a minute and work through that. If you did it correct, you should have the same answer. You should have the same answer. If you did not get the same answer, let's take a look real quick and see what happened. If you integrate with respect to x first, x squared becomes 1/3 x cubed, right? If you plug in 3, that's going to be 27 times a third, which is 9, so 9y. Plug in 0, it's going to just stay 9y, right? And now if we integrate 9y, that'll be 9 over 2y squared from y equals 1 to y equals 2. So 2 squared is 4, we get 18. Minus 9 over 2, and that should be 36 minus 9 is 27 over 2. Okay, if you made a mistake, was it a silly one, I hope? Okay. So, sure it was, okay. This is not a coincidence that it's the same answer. This is called Fubini's theorem. And not Houdini, Fubini. This is pretty much all he's known for. I think if my memory serves me right, this is like his big which is more than I've contributed certainly, but he's not like a Gauss or any of those guys that have just a ton of work in all these different areas. But basically,
all he did was like 2 double derivatives.
well, I mean that's kind of generalizing it, but I mean I'm sure he did other things, but this was due to him. So let R be, and this is the key here, a rectangular region defined by x being between a and b and y between c and d. If f of x, y is continuous on this rectangle, then the order of integration is interchangeable. So you could do the double integral over a region, in this case a rectangular region R, either with respect to x first and then y, or if you prefer, and you'll see why you might want to switch things. I mean, here it doesn't really matter. It's not harder one way or the other, but there are going to be times where you're going to look at an integral and you're going to go, you know what? I don't really like the way this is working out. Let me switch the order here. Maybe it'll make things easier. Okay, and we'll take a look at that in a sec. So interchangeable as long as you have a rectangular region for your region R. Okay, eventually, I mean, and you can, if you look back at the notes, our picture, our region R was not a rectangle. It could be any kind of region. It could be a circle. It could be bounded between curves. But we're going to start basic in this section, so we're sticking with rectangular regions to start. Okay. Why don't you guys try this example? I don't think there's any switching necessary, but just to kind of clear up notation, because there's different ways that they could ask you to do the same thing. So just try this one. Let's see if we can have almost, let's say, 95% or more of you get this one right. That'd be nice. It'd be even nicer if all of us got it right. So here we're evaluating this double integral with R being defined from 0 to 2 and 1 to 2. What do you think this notation means here? So 0 to 2 indicates what variable? Right. So this would be 0 to 2 in the x and 1 to 2 as far as the y's. Does that make sense? Okay, so again, different representation, but same idea. So set it up. Give you a minute or two here. And after we're done with notes, maybe I'll pull up Maple if we have time so we can see what's going on here.
If we call this one x and this one y, or this one y?
It does matter. It has to be in that order.
Okay,
Yes.
so it has to be x.
The first rectangle, first window, so to speak, will be x always.
So,
So if you're going with respect to y first, it just stays. What if that was a 2? Wouldn't that be like 2y? So basically this x gets y. So the x1 that would be. Pretend it's a constant. Oh, we're looking at. Fubini's theorem. Okay, again, I'm seeing very different answers. This could just be we haven't done integrals in a while, and that's okay. It should be negative 12, I think. Yes. So let's go through it. Since I don't see any issue with any particular order, I went dy first. So this will be from 1 to 2 and then 0 to 2. If I integrate with respect to y first, this x becomes xy, and then this becomes y cubed. And that's from y equals 1 to y equals 2. Plug in the 2. Now we get 2x minus 8 minus, plug in the 1, x minus 1. Clean it up a little bit. That's just x minus 7. The integral of x is 1/2 x squared. Integral of 7 is 7x. That's from 0 to 2. Plug in the bounds. So that'll be 2 minus 14, and then that part's negative 12, and I think you just get 0 the second time around, right? Does that make sense? Was it silly errors again? Okay, I think it's just a matter of you haven't integrated in a long time, so that's okay. All right. You'll get the hang of it. So the last thing we want to do, and then I'll hand back your exams. Let's take a look at this example. Let's say we have the double integral of y times sine of xy dA. Our region R is 1 to 2 by 0 to pi. Okay, so let's just kind of let's say I go dy first again. So if I go dy first, we have an issue if we go with respect to y first, don't we? Because we have a sine function with a y, but we also have a product with a y on the outside of that, right? So that could get pretty nasty. I mean, you could certainly do integration by parts and try it that way, but maybe not the best option here. So let's go the other way. Let's see what happens the other way. So if I go the other way, with respect to x first, I have the sine of xy, and then the chain rule would give me a y. So actually that's pretty nice there, isn't it? What's the integral of sine? What is it? Negative cosine. So negative cosine xy. And again, just make sure you're on the right track here. If you take the derivative of negative cosine, you get sine xy. And then if you do the chain rule on the inside, the derivative of xy with respect to x is y. So this is the integral right here of that first step. Okay? And now this is from x equals 1 to x equals 2 dy. A lot of space there. So then we get negative cosine 2y minus negative cosine y. So that's just, let me clean that up, minus cosine 2y plus cosine y dy. The derivative of negative cosine, I'm sorry, the integral of negative cosine of 2y, what would that be? Negative half sine 2y, and the integral of cosine is just sine, and that's from 0 to pi. Pi or 0, the sine of, well, it's really 2 pi, both of which are going to be 0, right? So the integral for this is 0. Okay, so basically in this section, you have rectangular regions only. We'll deal with curves and other kinds of regions tomorrow. You can integrate in whatever order you want. Just be careful. Sometimes one order might be a lot easier than the other. That's the big picture today. And certainly make sure you know how we got the definition and all the notation.